For this video, I'm going to show you how to solve equilibrium type problems involving the concept of solubility, or KSP. Generally, when we see these types of problems, there's really four different types of problems we can see here. You could be asked to calculate the KSP or the molar solubility, and that's just a basic problem using ice tables, and solving for X would give you the molar solubility. They could also ask you if a specific substance will precipitate or not, and there's a specific set of steps that you have to go through for those types of problems, as you can see here. There's also the common ion type problems, where you actually are mixing a substance that has an ion in common with the substance that you're looking at in terms of the solubility. So we can look at problems like that. And there's also a which precipitates first type of problem, where you're looking at two substances and you're trying to figure out which one will actually come out of the solution first. So these are the four problem types that we are going to look at and go through, and you'll see how to solve each of them. So the first type of problem we're going to look at here are the molar solubility practice problems. And this is the one that's probably most familiar to us because we did problems like this during solutions. We just didn't use the ice tables, but these can be done using equilibrium and ice tables as well. So in this problem, it's telling us the KSP value for CuIO32, and they want us to find the solubility at this particular temperature. So the first thing we got to do is actually write our equilibrium reaction here. So we know that the solid compound here, the CuIO32, all right, will be in equilibrium with each of its ions. So you have Cu2 plus, which would be aqueous, and 2IO3 minus, which would also be aqueous here. All right, so that's the reaction we're essentially looking at. The solid compound is dissociating into its ions in water. So we can set up our ice table for this particular reaction. All right, just remember here that for the solid compound, it does not participate in the equilibrium ice table. Remember, solids do not participate in our equilibrium constant. So we only need to worry about the aqueous products here. So initially, we know that each of these are not present. So they're both zero initially. Since they're not present initially, they're going to be forming. So the Cu2 plus change would be plus X, and the IO3 minus would be changing by 2x here because of the stoichiometry with the 2IO3 minus. So then we can apply these values now at equilibrium. 0 plus x is just x molar, and at equilibrium the IO3 minus would be 2x molar. So now we have our ice table filled in, and we can go about solving this. The first thing we want to do, though, is we want to make sure we write our equilibrium constant expression here. And since this is a KSP, we know it's going to be KSP is equal to the concentration of Cu2 plus times the concentration of IO3 minus here, but squared. That's your products. And then we don't put anything on the bottom here because our reactant is a solid. So that is our equilibrium constant expression here. So we can plug in what we know. We know that the KSP, according to the problem, is 1.4 times 10 to the minus 7. And this would be equal to the concentration of Cu2 plus, which according to our ice table is X, times the concentration of the IO3 minus, which we know is 2x, but we have to square it because of the equilibrium constant expression. So when we actually start combining these things here, we get 1.4 times 10 to the minus 7th equals 4x cubed. You can divide both sides by 4, and we get 3.5 times 10 to the minus 8th equal to x cubed. Take the cube root of both sides, and we get x being equal to 3.3 times 10 to the minus third molar here. And because the molar solubility is X in these problems, I know the solubility of the original compound. So this value here would be the concentration of my CuIO3 2. All right, this is my molar solubility. This would also be the concentration of my Cu2 plus because that's X, but 2 times this value would be the concentration of my IO3 minus. So that's how you go about solving a problem using ice tables and equilibrium concepts for a molar solubility type problem. So the next type of problem we're going to see here is what I call a Willet precipitate problem. These are problems where you will need to compare Q to KSP to figure out if a particular substance will precipitate or not. Just remember here, for these types of solubility problems, the general reaction that we're looking at is we have some form of solid in equilibrium with its aqueous ions here, essentially acting as our products. So the solid is like the reactant, and the aqueous ions or the dissolving is actually our products. So if you compare Q to KSP and it's less than, if Q is less than KSP, if you remember the alligator from class, that means the reaction is going to favor the product side, or you're going to need to form more products to reach equilibrium. So if Q is less than KSP, that basically means you're unsaturated because the equilibrium is going to go or form more of your aqueous substances, or it's going to dissolve more of your solid and form more of those products. So you're unsaturated. More of the solid can dissolve. If Q is equal to KSP, well, then you're at equilibrium. And then if Q is greater than KSP, if you follow the alligator, that means you're going to need to go to the left side or form more of your reactant, in this case, the solid, which that basically would mean you're precipitating out. So if Q is greater than KSP, that's when a precipitate will form because the equilibrium will essentially shift to the solid side, or more solid will come out. So that's what we're looking for here when we do these types of problems. We need Q to be greater than KSP in order for a precipitate to form. So here's just an overview of the steps you will see in a Willet precipitate problem. And I'm going to show you how to actually do one of these problems. So the first thing you do is you figure out which ions will actually form the precipitate. And then you need to figure out the number of moles of each of the ions in the precipitate. But you really do need to pay attention to the overall number of the ion in the compound that you're given. So that's something we got to watch for when we're doing these problems. Once you have the number of moles of each of the ions, you need to put the moles over the total volume of your new solution after you mix these things. And that will give you a concentration of each ion, which you can then plug that concentration into the Q expression here, and then you can compare what you get for Q to the KSP they gave you in the problem. So we're going to do all of these steps in a Willet precipitate problem. And remember, if Q is greater than KSP, then a precipitate will form. All right, so if we look at a Willet precipitate practice problem here, in this example, you can see it's asking, will a specific substance precipitate given that you're preparing it from a certain number of milliliters of a concentration of CeNO3 added to a specific amount of an MgIO3 And they want to know here, will this substance precipitate or not? So we're going to have to follow the steps. So the first thing is, if you look at the steps, was we have to figure out which ions are actually in the precipitate. Well, I can see here the substance they're asking me about. So I know that the CeIO3 is the substance they're asking me about in terms of the precipitate. So the ions that are involved here are the Ce3 plus and the IO3 minus. So they're the only substances I care about in the actual substances that they gave me here. So the first thing I need to do once I know the substances involved in the precipitate is to find the moles here of each of those substances. So For the first substance, I know that I have 750 milliliters of it. I need to figure out the moles here, so I'm going to need to get rid of the milliliters. There's 1,000 milliliters for every liter. And now that I have liters, I can use my concentration. I know that there's 4.00 times 10 to the minus third moles here. And this is the number of moles of my CeNO3 according to the concentration. Okay, and that's the number of moles for every liter because it's a concentration. So my liters cancel, and now I'm in moles of the compound. But you remember, we need the moles of the ion in this particular compound. So I only care about the Ce3+. So for every 1 mole of the compound, essentially, how many moles or how many Ce3+ are there in the compound? Well, there's only 1 moles of the Ce3+. There's only 1 Ce3+ in the compound. So my units cancel here, and now I'm in moles of the Ce3+. So when I calculate this, I get 0.00300 moles of the Ce3+. Well, now I need to do the same thing here, but now for the other substance that I care about, the other ion I care about is the IO3-. So I know that there's 300 milliliters of that substance. Again, there's 1,000 milliliters for every liter. This will allow me to get to liters so I can use my concentration. And they're telling me there's 2.00 times 10 to the minus 2 moles, but this is the number of moles of the MgIO3 and there's that many moles for 1 liter because it's a concentration. So my liters cancel. I'm now in moles of the compound, but again, I need moles of the IO3- ion because that's what's involved in my precipitate. So I know now that for every 1 mole of the compound, the MgIO3 here, there are 2 moles, according to the formula, of the IO3-. Okay, so that's what we mean by pay attention to the number of the ions in the compound itself. All right, so there's 2 IO3- essentially for every one of the compound. So when I solve this for moles, I get 0.0120 moles of the IO3- here. All right, so I found the moles of each of the ions in the precipitate that I'm being asked about. So now what I have to do, if you look at the next step, is you have to find or divide this by the volume because we're trying to get to concentration of each of these ions. So if I look in the problem, okay, I mixed 750 milliliters with 300 milliliters. So that is a total of 1,050 milliliters for my new total volume of solution. So essentially, there's this many moles of Ce3+ floating around in 1.05 liters of solution. Essentially, it's 1,050 milliliters. I just converted it to liters so that I can quickly find the concentration or moles over liters here. So you do need to be in liters because you want to find the concentration, but you got to total up the actual number of milliliters you're mixing. And then the IO3- is floating around in the same number of liters here. So now I can find the concentration of each of these. So the concentration of the Ce3+, when I solve for this, ends up being 0.00286 molar. And then the concentration of the IO3- ends up being equal to 0.0114 molar. So now I have the concentration of each of the ions in the precipitate that I care about. I can move on to the next steps of this type of problem. So now that I have the concentration of each of the ions in my precipitate, I need to plug that into the Q expression. So before I do that, I want to write out the actual reaction here for my dissolving of the compound itself. So I have this CeIO3, which would be a solid, in equilibrium with each of its ions, the Ce3 plus, all right, which would be aqueous, plus the 3IO3 minus here, and that's aqueous as well. So I can write the Q expression from this as being Q would be equal to here the concentration, remember products over reactants, so the Ce3 plus times the concentration of IO3 minus cubed according to the Stoic. And now what I can do is the concentration of these ions that I found previously, I can plug into my Q expression here. So when I do that, we plug in those concentrations. So we have the Ce3 plus was 0.00286, and the IO3 minus is 0.0114, but that is cubed. And when I solve this, I get 4 times 10 to the minus 9th as my value of Q. So when I compare these now, I have 4 times 10 to the minus 9th for my Q, and I have, according to the problem, 1.9 times 10 to the minus 10th for my KSP. So when you compare these numbers, the Q, because it's minus 9th, is actually greater than the KSP, which is minus 10th. So according to this, if you follow the alligator, the reaction is going to shift to the left side, or more of the solid is going to form. Therefore, yes, a precipitate will form. Okay, so I know all you're really answering is yes, a precipitate will form, but you do have to show all your work to prove this. So you need to find the number of moles of each of the ions in the precipitate, find the total volume of the solution, and then you find the concentration of each of the ions, and then you can plug that into your Q and compare Q to KSP. If Q is greater than KSP, then a precipitate will form. The next type of problem we see here are problems involving a common ion, or the common ion effect. The basic gist of this is that there is always a reduction or a lowering of the solubility of a precipitate whenever you add or mix in a compound that has a similar ion in it. So basically, you are adding a substance that has an ion in common with the precipitate you're looking at. And that will therefore lower the solubility of your substance. So it won't be as soluble because of that common ion that's there. So anytime you see a similar ion being added to your precipitate here, you are always going to have a reduction in the solubility. So we ignore the ion that's not common and focus on the common one. So if you can see in the little example here, it says if you add 0.10 molar NaCl to a solution of AgCl, the Na plus ions in the NaCl have no effect here because they're not in the AgCl. But now essentially you're adding more Cl minus ions. So this affects the solubility. So the AgCl, because of the presence of more Cl minus ions, is not going to be as soluble. So it's actually going to precipitate out some more. So less of the AgCl will be dissolved. That's a common ion effect. The substance here, the AgCl in this case, is less soluble than it was because of the presence of another Cl minus ion, or more Cl minus ion. That's the common ion effect. So let's look at an example of a common ion effect problem here. So in this case, this wants us to find the equilibrium concentration of the Mg2 plus in a solution of MgF2, and they gave me the KSP for it, but they're telling us we have 0.100 moles of solid KF being added. We're assuming that the KF dissolves completely and that any volume change associated with the addition of a solid here is negligible. Okay, so our volume is essentially staying the same. So you can see here that this is not like exactly like a molar solubility problem because they're telling us they added something to this, all right? But it's going to be very close to one of those molar solubility problems that we saw earlier, okay? So the first thing we need to do here is realize, hey, look, we need concentrations, all right? They're telling us that we're adding 0.100 moles of the solid, but our overall volume is 1 liter. So essentially, we know that we have 0.100 moles in 1 liter. So our concentration when we add the KF is going to be 0.100 molar. So it's very important. Just be careful with how these problems are worded. If they give you moles, pay attention to the number of liters you're dealing with. You do need a concentration here. All right, so now that I have my concentration, I need to actually write out my equilibrium solubility here. So essentially, I have my MgF2 here, which is my solid, and that is in equilibrium, all right, with its ions, the Mg2 plus, which would be aqueous, and 2F minus, which is also aqueous. All right, so that's the actual reaction I'm looking at. I can set up my ice table, okay? Remember, the solids do not participate in the ice table. They don't participate in equilibrium here. So initially, I don't have any of the Mg2 plus, but then here's the difference, okay? In a common ion problem, one of your initials is not 0. This is different from the molar solubility problems we did, where both were starting at 0. So in this case, we added Kf. F minus is the common ion. So instead of having an initial value of 0, we actually have an initial value of F minus as being 0.100 molar from the common ion. So that's the big difference in a common ion problem. Both of your ions are not 0. One of them is going to have a starting value, and it's going to be based on the common ion of the substance that's being added. So in this case, Kf was added, and F minus is the common ion, and we know the concentration of that. We already found it. So that is the initial value of our F minus. And then everything else here is pretty much the same. If we look at our change in concentration, we know we're going to be forming products here. So this is going to be adding some value of X. This one's going to be adding some value of 2X. So at equilibrium, this would be X molar, and this would be 0.100 plus 2X molar. Okay, so don't forget here that we had a starting value for this one, so it's not just 2X. So now I can write my KSP expression here for this. I know KSP would be equal to the concentration of my Mg2 plus times the concentration of my F minus squared here. All right, so now when I plug in the values here, I know I had a KSP of 7.09 times 10 to the minus 9th, and that would be equal to X for my concentration of Mg2 plus, and then my concentration of F minus is 0.100 plus 2X, and this would be squared. Now, because the KSP here is times 10 to the negative 9th, we can assume that any change here would be negligible, so we can always usually eliminate the plus X amount here from one of those ions. So that's good. It makes our math here a little bit easier. So when I solve this for X, and you can go through and do the math, but when I solve this for X now, remember, don't forget to square your 0.100. When you actually solve this, you should get 7.09 times 10 to the minus 7th molar. All right, and because they're asking for the concentration of the Mg2 plus, according to my ice table, the concentration of the Mg2 plus is X. So now that I found X, I know that that is the concentration of my Mg2 plus. So that's how you go about solving one of these common ion type problems. Very similar to the molar solubility problems, with the exception of you're going to have a starting value for, or an initial value for one of your aqueous substances, and you can eliminate, usually because the KSP is very low, you can eliminate your X in your calculation for the addition here. So that is a common ion type problem. So the last type of problem we're going to look at here is a which precipitates first problem. Basically, you will be trying to figure out which substance will precipitate out first whenever you're adding a particular substance to it. So these have a specific set of steps as well. The first thing you do is you write the KSP expressions for both possible precipitates. You substitute in all known values, and then you solve for the concentration of the ion that's being added here. Essentially, that's your unknown. And the idea here is that when you say which one will precipitate first, when you calculate these concentrations, you will obviously reach a lower concentration as you're adding a substance before you would reach the higher concentration. So the one with the lower concentration will precipitate out first. Typically here, we're going to have to do calculations, but if no calculations were required and the substances form the same number of ions when they dissolve, you can just look at the KSP, and the one that has the lower KSP will precipitate first. But like I said, typically we're going to have to show our work and show the process here. So we don't see that too often. All right, so in this example, they're telling us that a solution contains a certain amount of Cu plus ion and Pb2 plus ion. And they're saying we're adding some source of I minus gradually to this solution, and they want to know, will PbI2 or CuI precipitate out first? And they also want us to give the concentration of the I minus that will be necessary to make these substances precipitate. Okay, so according to the steps, the first thing we do is we write the KSP expression for each of the possible precipitates. So first, I know I have my PbI2 here, right? That would be my solid, and it would be in equilibrium with its ions, which would be Pb2 plus and 2I minus here. And my other possible precipitate is the CuI here, and that would be in equilibrium when it dissolves with its ions, the Cu plus and the I minus. All right, so when I write the KSP for the PbI2, the KSP would be equal to the concentration of the Pb2 plus times the concentration of the I minus squared, and the KSP for my CuI would be equal to the concentration of my Cu plus times the concentration of the I minus. All right, so I wrote the KSP expression for both of my possible precipitates, and now what I do is I plug in what I know for each. So obviously I know the KSP value here. We'll start with the PbI2 side. This is 1.4 times 10 to the minus 8th. All right, they told me the concentration of the Pb2 plus. If they didn't give me the concentration of the Pb2 plus, I'd have to find that depending on how this problem was set up, but they gave it directly to me in this. So I know the concentration of the Pb2 plus is 0.0020, okay? But I don't know the concentration of the I minus because that is what we are adding here. Okay, we're adding the I minus to the solution. So I'm trying to figure out the concentration of the I minus that would make this precipitate out. So when I solve this for the concentration here of the I minus, so you do the math here, you should end up getting the concentration of the I minus to be equal to 2.6 times 10 to the minus third molar. Okay, so that is the concentration of I minus that would be needed here to precipitate out the PbI2. So if we look at the CuI now, I do the same thing, plug in what I know. They gave me the KSP to be 5.3 times 10 to the minus 12. And they told me the concentration of the Cu2 plus was 1.0 times 10 to the minus 4th. But again, I don't know the concentration of the I minus because that's what I'm solving for. So when I do my math here and solve for the concentration of the I minus, I get it to be 5.3 times 10 to the minus 8th molar. So let's just review here what we did so far. We wrote the KSP expression for both possible precipitates, plugged in the values we know, solved for the concentration of the unknown, or the one we're adding. So now what we do is we compare these two. All right. Obviously, if you were slowly adding I minus to this solution, okay, the concentration of the I minus would slowly start to increase. All right. So the lower concentration of these two would be reached first. So if I compare the two here, the CUI would actually precipitate first because its value of when the CUI will precipitate is when I minus has a concentration of 5.3 times 10 to the minus 8th, which is lower than the concentration of the I minus needing to be 2.6 times 10 to the minus 3rd for the PBI2. So the CUI is going to precipitate first here because its concentration is lower for the I minus, and that concentration would be reached first, so it would precipitate out long before the PBI2 would, because the PBI2 needs to reach a concentration of I minus to be 2.6 times 10 to the minus 3rd before it could do it. But then the follow-up question here is that it wants us to specify the concentration of I minus necessary to begin the precipitation of each salt. Well, we already did that, okay? This is the concentration of I minus needed to precipitate out the PBI2, and this is the concentration of I minus needed to precipitate out the CUI. All right, so that's how you do a which precipitates first problem. Write the KSP for each of your possible precipitates, plug in what you know, solve for the concentration of your unknown or the substance is being added, and the lower value of your substance being added will be reached and therefore precipitate out first. So just a recap here of the different problem types that we could see. You could be asked to find the KSP, or molar solubility. That's where you use an ice table. Very important to figure out here which ones you actually use ice tables for. You use an ice table for this. You don't include your solids in the actual ice table calculations. And when you solve for X, X is the value of the molar solubility. You could see Willet precipitate problems. And for those types of problems, we do not use ice. So no ice table for the Willet precipitate types problems. You simply find the number of moles of each of the ions in the precipitate. Pay attention to the number of the ion in the actual compound you're dealing with. You figure out the concentration of each of those ions, and then you plug the concentration into your Q expression and compare that to KSP. If Q is greater than KSP, a precipitate will form. We also have common ion type problems here. Again, common ion problems, very similar to molar solubility problems. So you do use ice tables here. You are allowed to use the X approximation where we can cancel out our added value of X because usually these have a very low KSP. The only difference here really is that one of your ions in your ice table will have an initial value. Okay, so you will have an initial value for one of the ions in your ice table initially, and that changed the problem a little bit, but otherwise it's pretty similar. And the solubility of the substance you're dealing with is always lower because of the addition of a common ion. And then the last type here is a which precipitates first problem. Again, this type has no ice tables involved. Okay, you write the KSP for both possible precipitates, plug in your values, solve for your unknown concentration, and the unknown that has a lower concentration would be reached first and therefore precipitate out first. So those are generally the types of problems we will see involving equilibrium with solubility and KSP.